To operate autonomously over long time horizons, an AI agent requires a partially observable Markov decision process, or POMDP, belief state. This functions as an internal, sufficient statistic of the interaction history, a compressed representation of events organized specifically to drive the next decision. The standard engineering approach to building this belief state is straightforward. Simply append every historical log, user message, and system action into an ever-expanding LLM context window. This creates an immediate mechanical failure. Even in models boasting 100,000 token limits, attention dilutes across the sequence. The model reliably loses focus on critical data placed in the middle of these long logs. To manage these hard token limits, engineers rely on rolling summaries, compressing older history to make room for new data. This introduces a second flaw: summarization drift. With each compression pass, the model extracts the broad narrative and discards the details. After 3 or 4 cycles, low-frequency, high-importance edge cases, like a single warning not to execute a specific API call, are permanently deleted from the agent's historical record. Relying on the active context window to serve as long-term memory guarantees the gradual degradation of the agent's knowledge. The system corrupts the fidelity of its own historical record over time. The standard industry alternative to massive context windows is chunking those historical logs into a monolithic vector database for retrieval augmented generation, or RAG. Vector stores operate on a specific mathematical premise. They map and retrieve data strictly based on semantic similarity, grouping records by their associative proximity to the user's prompt. Associative proximity only captures what happened. It destroys the mechanistic dependency between events, stripping away the sequence and cause of the actions. Complex, multi-hop reasoning requires an agent to know exactly why a decision was made, or when an event occurred. It cannot solve problems by pulling isolated text blocks that share keywords. By retrieving structurally irrelevant distractors, like logs containing the word crash, semantic search feeds the agent noise. It entirely misses the distant data point representing the actual causal trigger. Flat semantic proximity fails to construct the logical pathways required for complex problem-solving. The empirical countermodel to flat vector stores is Magma, the multi-graph-based agentic memory architecture. Magma discards the monolithic bucket approach entirely. Instead, it structures memory as a time-variant directed multigraph, decoupling the data into distinct relational views. This bottom layer is the semantic graph. It maintains standard undirected edges, connecting conceptually similar events based on their cosine similarity. The structure then moves up to the temporal graph, which acts as the immutable chronological backbone of sequential events, ensuring a strict timeline. The third layer is the causal graph. This maps explicit logical entailment, with directed arrows jumping across the timeline to ensure causes strictly precede their effects. The top layer is the entity graph, which links disparate events to abstract object hubs. This preserves object permanence across disjoint timelines, keeping track of specific people or systems over weeks of interactions. By maintaining these 4 orthogonal views simultaneously, the agent is no longer guessing based on keyword overlap. It can trace the exact architectural logic of its own history. Computing complex causal and entity graph relations requires heavy LLM processing. Executing this during a live interaction will destroy an agent's real-time response latency. Magma solves this computational bottleneck using a dual-stream write path. This decouples raw event ingestion from LLM-driven graph consolidation. In the synaptic ingestion stream, or fast path, incoming data instantly locks into the linear temporal backbone and a vector index. It bypasses complex LLM analysis entirely. This fast path guarantees strictly order-of-one blocking time. The agent remains highly responsive to the user, storing the immediate experience without pausing to calculate its broader meaning. The deeper reasoning is offloaded to the slow path, an asynchronous consolidation process acting as a background LLM worker dedicated to densifying the graph structure. In the background loop, this worker sequentially dequeues ingested events and analyzes their local node neighborhoods. It draws deliberate causal and entity edges between previously unconnected points. This architecture perfectly trades asynchronous compute time for deep relational structure. It keeps the agent fast in the moment while making it smarter over the long term. With the graph constructed, the challenge shifts to the read path. how the agent retrieves the exact context it needs from this dense multigraph without simply downloading the entire database into its prompt. Instead of running brute force similarity lookups, Magma executes a policy-guided graph traversal. The retrieval process starts at the query router. The router decomposes a user's prompt to classify the specific cognitive intent behind the question. This intent tag generates a dynamic weight vector that biases a heuristic beam search. For a why query, the causal edges in the multigraph glow brightly and thicken, while the semantic edges fade to gray. The search algorithm is now mathematically forced to traverse causal chains and entity consistency paths. It actively ignores semantically similar but structurally irrelevant distractors. Explicitly decoupling memory representation from retrieval logic allows the agent to construct highly precise, intent-aligned contexts. It isolates the exact logical pathway, completely free from the noise of standard semantic search. We can measure the empirical payoff of Magma's architecture using the Locomo long-context conversational benchmark. This chart shows the overall accuracy scores across memory models. Explicitly modeling multi-relational structures drives massive outperformance in adversarial and temporal reasoning. Magma reaches 0.700, significantly outpacing flat memory systems like Nemori, Memory OS, and AMEM, which all hover between 0.550 and 0.590. To isolate exactly where Magma's reasoning capabilities originate, researchers conducted a systemic ablation study, disabling one layer of the graph at a time. When deleting the causal edges from the system, a linked metric measuring multi-hop accuracy immediately drops. When the temporal edges are deleted from the graph, the agent's temporal accuracy plummets. The ablation data confirms that no single relation type is sufficient on its own. Advanced agentic reasoning requires the intersection of orthogonal historical views. Beyond pure accuracy, we have to look at the critical engineering metric of system efficiency. This is tested using the long MEM-eval ultra-long context stress test. Relying on context-resident memory carries a prohibitive computational cost. Full context baselines consume over 100,000 tokens per single query just to maintain their accuracy. This scatterplot compares token cost on the y-axis against accuracy on the x-axis. Full context sits high on cost and medium on accuracy. Magma appears at the extreme bottom right, achieving superior overall accuracy while consuming an average of only 3,300 tokens per query. The architecture achieves higher reasoning capabilities while driving a greater than 95% reduction in token consumption and inference time latency. The next generation of autonomous AI will not be defined by which lab can build the largest context window or the biggest vector database. The true bottleneck is architectural. Agents will be constrained by how rigorously they map the mechanistic dependencies between their own experiences. The next stage of autonomy depends on the